Okay, it all went quiet. I think that means I talk. So, welcome everyone. This afternoon, we're going to talk about a fairly radical new approach to thinking about software architecture. So, I've been working in the industry for about 25 years, and I'm just about to finish a PhD in the subject of complexity science and software engineering, fusing the two of those things together to give us something a little bit different. That's what we're going to talk about here today. So the problem that we're trying to solve is very simple. Why is software architecture so difficult? In 1968, there was a big conference in Garmisch in Germany where a whole bunch of leading lights in the software industry got together and said, why is this so difficult? Why do we keep screwing it up? Why do we never deliver on time? Why does it never work properly? And that was a very long time ago, and we're still kind of asking the same questions today. Why is it difficult to do? Why is it difficult to teach? And that's the problem that we're trying to solve. When you scrape at the surface a little bit, you'll find out that there are three major things that cause us issues in software architecture, and they're all related to each other: time, change, and uncertainty. Time is important to us as architects because the architecture that you deliver today for your project will not look the same 6 months from now, it will not look the same 2 years from now, and it definitely won't look the same 5 years from now. Our architectures change over time. But when we represent our architectures, they're always static diagrams, frozen in time. An architecture is a bunch of lines and boxes. There's no way for us as architects to represent this time or the change that's going to happen over time. And the reason that it's not represented is because it's far too difficult for us to even talk about. Because we don't know what that change is going to be. We don't know when it's going to happen. We don't know the nature of that change. So what we do is we sweep it under the rug and we continue to deliver static architectures and static architectural diagrams. This is what makes architecture difficult. If this problem went away, we wouldn't need architecture. We wouldn't need to think about it. We could just write code and be happy. But that's not going to happen. So another problem that we have is this idea of the unit of software architecture. What is an architecture made of? What is the base unit of an architecture? And this is a very old question. You can go right back to ancient Greece, where a number of thinkers talked about the idea of arche. What is the root of everything? What is the first principle? What do we build upon? And the Greeks came up with some very strange ideas about this. They thought that everything was made of earth or fire or wind or water or a combination of these things. And these ideas seem a little bit silly in retrospect, but asking the question was the important thing that the Greeks did. What is everything made of? This eventually leads to ideas like the atom or the Newtonian particle. And once you have that idea of the unit, you can build an entire science around that one foundational principle. You see this in physics, of course, but also in chemistry with the idea of a molecule, and also in biology with the idea of the cell. Software engineering has been on a bit of a journey. We have a lot of potential units, and we like to talk about them, and we like to debate them, and we like to get perhaps a little bit religious about them from time to time. One of the things that makes the model of physics so compelling is that a bunch of physicists can gather around the idea of the atom, and they can all work together and discuss the world around this unified foundational principle. When you gather a bunch of architects around a table, they're all coming from a completely different starting point depending on where they've been in their careers and what they believe in. And this makes it really, really difficult for us to move forward as a serious grown-up profession with a scientific foundation. This combines with time, change, and uncertainty to make things very, very difficult for us as software architects. This session is going to introduce a brand new unit, and that unit is called the residue. And the residue is a building block for our software architectures that allows us to capture time, change, and uncertainty in a way that makes it easier for us to work with these things. There's a couple of things we have to understand before we dive into this conversation. The first thing is the difference between order and disorder. So a system is a fancy word for a bunch of stuff connected to other stuff. Some systems are ordered, and ordered systems are nice. They can be engineered. They're highly constrained. That means that the individual elements in the system don't have a lot of options because the other elements are stopping them, constraining them. And you can predict the future states of an ordered system. And you can test them, and you will see consistent behavior, hopefully, over testing cycles. And so a good example of an ordered system is a car. 30,000 parts in your average fossil fuel-driven car. They're all highly constrained by each other. They do roughly the same thing every single time you start the car, if it's not broken. By this definition, software is an ordered system. Now, if you've worked as a software engineer or an architect, that might seem a bit strange, because things are not predictable. Things are not ordered, but software itself is ordered. The thing that is disordered is the environment which we make our poor little software systems run in. The human environment is completely disordered. It's loosely constrained in that people do whatever they want. It's unpredictable, and while our minds are almost built to recognize patterns and we think we see patterns, they're usually an illusion, and they disappear and change over time. So human and business systems are disordered. And the job of the architect is particularly cruel. We go to university, we learn software engineering, we learn how to build systems, and we learn how to build ordered systems that have consistent and predictable behavior, that are reliable, that are robust in some way. And then we force them to live inside this bubble of madness, which is your average business, which is full of people and hierarchies and money and economies and social conditions and stuff that is just moving all the time. And once we put our innocent little software structure into this bubble, something happens. And that something, we just call it X, because we don't actually know what's going to happen. And the bad news about X is there's always more than one of them. And when they turn up, they're usually a surprise because no one told us about them. And the result of these X's is that they put a great deal of pressure on the software structure we've so lovingly designed, and they tear it to pieces. And someone will walk past after one of these X's has happened and said, "Why would you build it like that? That was silly." And it's easy with hindsight. The way we solve this problem in software engineering is pretty smart. We create a smaller bubble with less madness in it. It's a magical bubble, and we call it scope. And we say, all the X's that you tell us about are in scope, and all of the X's outside that, when they happen, then you have to pay us to build the system again. As a business model, this is unbeatable. So it's very, very hard to get software people to move away from this business model. The problem with this solution, of course, is that there is always an X. Regardless of whether you have a scope, regardless of how careful you are about the definition of X's inside that scope, there's always going to be something that pops up that you didn't know was there, that your business stakeholders didn't know was there, that's going to destroy your architecture and force you to rip it apart in ways that you didn't really want to. And it makes the structure fragile over time. If this was the way it always was, then there would only be one answer to this question. And that answer would be to wait for X to show up and then deal with it. And we've tried that. It didn't really work out. The problem becomes more interesting when you work for a long time and you realize that across our industry there's an enormous number of architects who consistently deliver architectures that survive this problem. And the question and the thing that has driven my research becomes, what are they doing? What are they doing that other people aren't doing? If you go and ask these architects who over long careers consistently solve this problem, how do you do this? What is it that makes you able to do this? They will inevitably tell you that they're magic. You won't get any more explanation than that. And the reason for that is they don't actually know themselves. And I got this question 15 years ago, how are you doing this? And I had to admit to myself, I don't actually know. And so this entire research project was me trying to figure out what actually happens in our heads when we work with software. And so this eventually led me to the conclusion that the difference between these senior architects and everyone else was that they were incredibly comfortable with the idea of uncertainty. When they went and met stakeholders and asked them, what do you want us to build? And those stakeholders said, we don't really know. They didn't panic, they didn't refuse to work. They just dealt with the uncertainty and they were comfortable with it. And this led me down the path of looking at the complexity sciences, which is a fascinating discipline that is entirely focused on how do you deal with things you don't understand and can't predict and can't control. There's a lot going on in the complexity sciences, so I'm going to give you an introduction with two concepts that are incredibly relevant for software engineering. The first concept is the idea of a random simulation. And this is how you gather information in a system where you're deeply uncertain about what's actually happening and you don't understand the rules that govern cause and effect inside a system. So if I show you this picture and I say, I have a square of side x, and inside that square, I have a circle. And my question to you is, what is the area of the circle? Most of us, because we were good at math, will immediately start to look for the radius of the circle and we'll be thinking pi r squared. That's how we get to the area of the circle. Unfortunately, in this case, that's not possible, mostly because the circle and the square are so badly drawn. The way we solve this kind of problem in the complexity sciences is we simply throw a dart at the shape. And my first dart lands here inside the circle. And then I throw another dart at the shape, and it lands outside the circle. And based on this random sample of information, I can say that the circle must be half the area of the square. So therefore, it's x squared over 2. If you're a deeply linear thinker, this just made you feel very uncomfortable. I think there's something very flaky going on here. It turns out that if 2 is ridiculous, right? But if you throw lots and lots and lots of darts, eventually you provably get very close to very accurate answers for the radius of the circle, and you can even deduce pi from this kind of calculation. There's little spreadsheets on the net. You can download this for. So the question becomes, when you're gathering requirements from your business stakeholders, are you doing pi r squared, where there's a definite formula that leads you to an answer, or are you just throwing darts at these poor people? And the answer is, we're just throwing darts. What you get from your interaction with stakeholders is a random sample of what's going on in their heads. And what's going on in their heads doesn't necessarily reflect reality out there. That's why X keeps popping up over and over and over again. The second concept from the complexity sciences that's really important is the idea of a Kauffman network. And this was a concept that was developed in 1966 by a biologist and a complexicist called Stuart Kauffman, who was trying to answer the question of how did life come to be? How did we go from a bunch of amino acids to the Beatles? How does that happen? It doesn't seem possible. And what he started to do was model the behavior of amino acids. And he came up with this concept, which is called a random Boolean network. And so each one of these little circles is a node in a network. And they're Boolean nodes. That means they have 2 potential values, 1 or 0. So a good way to think about these nodes is light bulbs. They're either on or off. And they're random because every light bulb has a tiny little bit of code in it, a different bit of code for every light bulb, that randomly decides, am I on or am I off? And so if you have a little switch down here, every time you press the little switch, you'll get a different pattern of light because the random thing will decide whether they're on or off. This system has a number of states. The number of patterns of light that you will see as you sit and press this little button will be 2 to the, because it's Boolean, to the power of n, which is the number of nodes in the network. Kauffman runs this experiment with n set to 100,000. 2 to the power of 100,000 is an impossibly large number for us to even contemplate. If your requirement specification has 2 to the power of 100,000 things in it, you're not going to get very far. Although the consultancy fees for writing that document might be pretty cool. Then he does something interesting. He adds links between the nodes, and he creates dependencies between them, so that when one node fires and it decides, I'm a 1 or a 0, it can tell its neighbor, if it feels like it, I'm a 1 or I'm a 0. And when its neighbor receives that input, it immediately recalculates with that as a parameter. And so when you press the button now, you see a little bit of blinking before it settles into its pattern. This is the way amino acids kind of behave. And he presses his little button and he notices something strange. The system, he starts to see patterns of light that are the same over and over again. He starts recognizing the patterns and he counts them. And it turns out there are only 317 patterns in this system that keep coming back. So we've gone from 2 to the power of 100,000, enormous, to 317. If there's 317 states in your requirement specification, that's still nasty, but it's finite, it's doable. We can work with it. You'll have already figured out by now that 317 is the square root of 100,000. There's one person nodding vigorously here. He's way ahead of me. 3 at the square root, so this number of states in this linked system is root n. And Kauffman calls these states attractors. And he took the inspiration for that word from Lorentz, who came up with the idea of a strange attractor because he was messing about with wonky pendulums a few years before this. He calls them attractors because it seems like the system is constantly pulling all the nodes back to this position, that the system is pulling them there. It wants to be there, and they're called attractors. And attractors then become a very, very important concept in complexity science. So the reason that we have birds and bees and bats, and they all have wings, is because of these attractors. The biological systems are being pulled back to the same states over and over and over again. It wasn't like they inherited that from each other or they copied each other. It just keeps turning up. The pattern keeps reappearing. And these reappearing patterns we call attractors are the only way that we can navigate the world that we live in. It's actually the only reason that we have the form that we have and don't collapse into a puddle of goop on the floor. He notices something about these attractors, which is where this starts to become really interesting for us as software engineers. There are 3 numbers that we can play with here that will influence the number of attractors that we see in a system. The first number is n, pretty obviously. The number of nodes in a system, as you increase the number of nodes in a system, the number of potential attractors in that system will start to grow. You'll get more and more attractors. So anyone who's played with microservices will realize this very quickly and very painfully. That as you increase the number of components, the number of potential states your system is going to end up in gets larger and larger and larger, troubleshooting takes longer, operations get angrier and angrier at you. The second value is K, and K is a measure of the connectivity of the network. How many links are there between the components in this system? Here I've taken the maximum K, which is 3. What he realizes is that as you raise K, not only do you get a lot more attractors, but the paths between those attractors start to become increasingly chaotic, and it takes much more blinking before the system settles down. If you've ever done any work in enterprise integration, you know that if you allow the connections between systems to grow without being managed or curated, you'll end up with chaotic interactions between the systems in your enterprise, and we tend to not do that as much as we used to. The third variable that he's noticed that we can play with to affect the number of attractors in these networks is something called bias, which he calls P. And bias works like this. If I have a node down here, and it sends a message this way 50 times out of 100, and this way 50 times out of 100, then that node has absolutely no bias. It's democratic in what it does. But if I have a node up here, and I influence it so that it sends its message this way 98 times out of 100, and this way 2 times out of 100, then we say that that node has a high degree of bias. And Kauffman realizes that if he raises the bias of the nodes, then he can raise n and raise k without the chaos appearing. And he can lower the number of attractors. In the software industry, we know about n, we know about k. P, the best example of P in the software industry, are the tenets of service orientation. We've learned how to restrict our components to say boundaries are explicit. We only communicate via contract and via policy and by defined schemas. We respond to errors and security calls in exactly the same way. All of that is biasing our components to behave in a certain way. So nothing that I've said now on this slide is new to you as software engineers. We've already figured this out, but we figured it out heuristically and painfully. We've never used this kind of work as a reference before. So based on what I've said, every software project from the perspective of a complexity scientist, every software project is a two-step algorithm. A random simulation of the environment followed by an analysis of potential NKP component structures that will survive in that environment. That's all we do. Complexity scientists solve big problems. They look on us as solving small, trivial things. We have a few things we need to work with here. We have a filtering bias that stops us from actually doing proper random simulation, and the NKP analyses we do are implicit. And so what we need is a theory that's going to help us make the simulation more random and make the NKP analysis more explicit. And with that, we come up with something called residuality theory. And this is a way of understanding how systems move and change. So we start off with a complex system, and we describe it as a little network. And we say to ourselves, let's stop for a second, because we're in the IT industry, let's stop with all the hype. Okay, let's stop with just saying things and pretending they're true. Let's only say things that we know for certain are true. When I have a complex system like this, a business system, what can I say about this system that is absolutely undeniably true in all cases? And the only thing I can say about this system that's absolutely undeniably true in all cases is that something is going to happen. That's all I can say. It sounds hopeless, but don't worry, it gets better. What is that thing that's going to happen? I have no idea. Let's just call it X. Something is going to happen, and I don't know what it is. The other thing we can say, be it just looking at the history of architecture and enterprise architecture, is that this complex system is so big and moving so fast and so complex that you can't map it, you can't write it down, you can't document it. What we can say that's also true is that when X happens, when the system changes, the system itself is going to change. It's going to be different. The network is going to look different. And we call this piece here, the thing that's left over after the change, we call that the residue of the system. It's the leftovers. I've had feedback from some developers that they don't like this word because it sounds disgusting. Fair enough. The only thing the residue itself is also a complex system. What can we say about that that's absolutely definitely true? Well, it's the same thing. Something's going to change. Let's call that X dash. I still don't know what it is, I just know that it's going to happen. But what I can say is that the next step in this process as the system moves is path dependent. It is going to depend on, it's going to be a function of that previous residue. The residue affects where we can go in the future. And so, from a software architecture perspective, there's two truths we have to be honest with ourselves about. We cannot map this system. It is too big, it's moving too fast, it has too many variables, it has too many possibilities. We cannot predict X, we cannot predict X dash. The only thing as a software architect that we have control over is the residue of the software part of the system. We have control over how that falls apart. That's all we've got. How depressing is that? It turns out that this has a happy ending. So, what have we learned? Let's go back to our original problem. I have this innocent little ordered software structure inside this complex mess. What have we learned? We've learned that we don't need to grab every single variable inside this complex mess and understand every single configuration and every single possibility. We've learned that there are a limited number of attractors inside a complex system that we need to be worried about. Most of the rest of that, so we're going from 2 to the power of 100,000 to 317. And so we can get rid of this big bubble, and we just have these little attractors that we have to worry about. That's it. That's much better. See, it's getting happier. How do we find out what those attractors are, though? That's the question. How do we find the attractors? I've already given you the answer. We throw darts at it. We just make something up. It's random. And so we come up with some X that's going to affect our system. Let's say that an example of that X is a competitor drops their price. When a competitor drops their price, there's a business reaction. There's an impact in the market. The business will change its offering, change its processes, change its suppliers, buy the competitor, do something. When that happens, we move into this little attractor, and then from the perspective of the attractor, I ask, what's my technical residue? What's left of my architecture in this residue, in this attractor? Does it break? Does it crack? Does it keep running? And the answer usually is no. This component and this component are blow up. You have to rip them apart, put them back together, reconfigure them. It's nasty. There's rework. You would consider this that my architecture has not stood up to the challenge of this change. But if in the initial architecture, if I'd had this little green component, we would have survived. And so what we do is we take this updated residue and we park it over here and we say, this is residue number 1. This is the first building block of my software architecture. We come up with another one. Let's say there's a drop in the price of aluminium. Do we survive? No, but if we had this little orange thing, we would have survived that. That's residue number 2. We do it again and again and again, and what we end up with is our original naive architecture and a whole bunch of residues, and these are the units. This is our architecture broken down into units with time and change and uncertainty being the thing that separates the units. And what we will then do is we will integrate all of these residues together into a single coherent architecture. And when we do that, we notice something very strange in the behavior of this architecture, if we've used a big enough sample. We'll notice that this architecture will start to survive X's that it hasn't been designed for. And that's pretty cool if you're an architect. That's the problem we have to solve. The reason for this turns out to be a really simple mathematical relationship that has existed the entire time we've been building software. We just didn't see it until now, and all those senior architects, they intuitively figured this out, but they couldn't explain it. This is what happens. When I have a residue in my architecture, that residue will survive in at least one attractor, by definition. It turns out that in practice, it usually survives in multiple attractors. Every one of those attractors will be linked to a large number of potential stressors, X's, that will push the system into that attractor by virtue of the 2 to the power of 100,000 versus 317 rule. There's a lot more X's than there are attractors. There's a lot more events that can happen in a system than it has attractors. And they push the system into that attractor. So all I have to do as an architect, and all you have to do is find one X. Just come up with one X. That one X will help me identify this attractor, which identifies this residue, which survives in all these attractors, which means it survives all of these potential X's. And so you can see that the actual probability of that X, the fact that the chances that it's going to happen, doesn't matter. As long as you find that one X, you will have a system that survives all of these things. And when that happens, you get to say, I'm magic. Because this looks like you've built a system that's surviving things that weren't done, that you are now surviving off-spec events. This is what we want to be able to do. I'll give you an example to make it a little bit more concrete. We're going to build a cloud-based platform that's going to manage an enormous fleet of electric car chargers across the world. And the way it's going to work, the naive architecture, our starting point, which like most naive architectures is going to get put into production, is that a customer will go into a website, sign up, give their credit card details, and we'll send them a little key fob home. They drive up to the charger, they hold up their key fob, it gets read, sends a message up to the cloud, looks up your subscription details, says, yes, you can charge, or no, you can't. Fairly simple system. And we start coming up with X's, and we call this process a stressor analysis, and we record the results of this work in a spreadsheet, so that every row in this spreadsheet that you see represents a stressor, an X that triggers an attractor, and what we have to do to augment our residue to survive in that attractor. That's what we're doing. There's a couple of things that are interesting here. Stressor number 3 is about the failure of the key fob. You drive up in your car, you hold up your key fob, and nothing happens. What's the attractor? The attractor is that you have a very angry customer who can't go anywhere because there's no electricity in their car. They can't charge their car because the key fob is broken. And you've got a queue of equally angry customers sitting behind them, and they can't get to the charger either. How do we solve this? After much debate and deciding that a call center is way too expensive, we come up with a different solution, which is called automatic license plate recognition. So we scan everyone's license plate as they come onto the lot. We allow them to charge, regardless of whether they have a subscription or not, just to get rid of them. It turns out to be cheaper to do that than to allow the queue to build up. And then, depending on what country you live in, you can look up the license plate, send them a bill home, offer them a membership. It actually lowers the cost of getting new members, and it allows people to just drive in and use the thing. The next thing that's interesting is number 8, where we have some kind of damage to our chargers. People are going to drive into these things. It's inevitable when you're driving and you're trying to line your car up. If you look at any petrol station, you'll see everything's dinged. The way to solve this is with a little bit of redundancy and some security cameras for insurance purposes. The next one that's interesting is down here, is number 12. This is a big problem. A customer will abandon their car, they'll drive up, they'll plug in the car, and they'll go away for a long period of time. This happens a lot at golf courses and shopping malls. This causes the same problem. No one else can get to the charger. You have frustrated customers. How do we solve this? We change our business model, and we start to invoice per minute. A fast charge, the whole business model is based on a fast charge taking 25 minutes. So after 25 minutes, if you're still plugged in, then you're going to start getting charged per minute on a sliding scale, which means that if you want to park there all day, you can, but you're looking at a very large parking bill, which surprisingly isn't a problem for a lot of people. But it still changes things. If people do this, we earn more money. That's pretty good. So far, we've stressed our way and we've changed our architecture, but it's kind of so what? This is normal business development. The interesting thing happens here with number 14, which is called icing, I-C-E. ICE stands for internal combustion engine. It's how the electric car industry talks about the fossil fuel-driven car industry. Icing starts to happen first in the United States. And what happens is people will park a fossil fuel-driven car in front of the charger. Sometimes because there's no parking space, sometimes because we don't know, we think someone who owns an electric car has a different political opinion than me, and we don't like those people, so we want to irritate them. And at least one incident, someone does this, parks in front of a charger, waits for a bunch of electric car owners to queue up and get angry, and then does a TikTok of themselves dancing in front of the angry electric car owners, puts it up on TikTok, it goes viral, and this happens everywhere. This is the kind of thing that you won't catch in a requirement specification. It's one of those 2 to the power of 100,000 things that can happen. But it turns out for this particular architecture, because we've stressed our way to it, a combination of number 3, which is automatic license plate recognition, that doesn't stop working because your car's not electric. We have your license plate. Number 8, we have redundancy. So if you want to damage us as a company, you're going to have to bring all your friends to do this. We also have security cameras for the police report because this is technically sabotage. And because we're invoicing per minute on a sliding scale, you'd better make this a very quick TikTok or it's really going to cost you. And we will make more money. And this is the kind of thing we see. This is off spec. This is not defined in the specification, but because we've stressed our way to the system, we're starting to survive these things. If you think that this is purely something that can happen in the United States, this is what happens in Munich, where someone using the same logic looks at an electric car, thinks this person has a much higher cares about the environment, has a much higher likelihood to be a vegetarian. So I'll show them, and they stick mincemeat in the device. And I don't care how good your architectural process is, I don't care how good your risk management is or your requirements gathering, you do not have someone will stick mincemeat in the device in that document. These are the things in complex, growing, changing systems that we simply can't capture, but we have protection against them. What we're actually doing is we're changing what we do as architects. As programmers, our goal is always to be correct. A program has to be correct. We've put a lot of energy into that over the years. That means that we have to get the same result every time, that we have to know what the initial conditions are, we have to know what's going to happen, we have to know what the result is going to be, and we have to know the relationship between cause and effect. As an architect, you don't have access to that world of the programmer, and you have to leave that behind. What the architect has to aim for is something called criticality. And criticality comes from Kauffman, where every system has a balance between n, the number of nodes, and k, the linkage between those nodes. And you can have a system with very high n, or very low n and very low k, a very low number of components and a very low number of links between those components. In software, we call that a monolith. In biological terms, any biological being with a small number of components and a small number of links between those components is very vulnerable to being killed because you just need to kill one of the n and the whole thing will die. So the way out of that is to have a much larger n and a much larger k, so that if you kill one of the n, the rest of the thing will keep on moving, it will keep on living. That's why we've got 2 lungs. But you can go too far with n and k. In our industry, we call this microservices, and we know you can go too far. We've all seen it. It gets to the point where n and k are so large that the number of attractors becomes so large that the system collapses under the weight of managing it itself. In biological terms, this turns up as cancer. In microservices, it turns up as Friday night debugging log files. Kauffman describes then that there's this magical line in between, this optimum in between the monolith and the microservice, which he calls the edge of chaos. You may have heard that before. And that's when you have high enough n and high enough k to be able to survive unforeseen things and regroup, but not so high that the system collapses under the weight of managing itself. What we're doing with this technique is that we're starting off down here with our naive architecture, and we stress it with a random x. And when we stress it, we have to add new components and new links, and n and k rises. And we stress it again, and n and k rises again. And we keep stressing it until we see, like we just did on that spreadsheet, that it starts to survive things that are off spec. As soon as it starts to survive things that are off spec, which we call looping, we're somewhere near this green line. And that means that we've produced an architecture that is critical. Now you can see there's lots of points on that green line, so there's still lots of options, lots and lots of different architectures that can solve the problem, but we have this property of criticality that we use to qualify whether or not an architecture is actually any good. And this becomes an incredibly useful way to think about what we're doing as software architects. It gets us out of the trap, the programming trap of always needing to be correct, because when you're dealing with these complex systems, correctness is just not accessible to us. It's not accessible to Western science, so it's not accessible to us. The big question then is, how do you integrate all of these residues together? Because there's a big risk that you're going to mess them up, that as you make them live in the same box, they're going to influence each other and they're going to give you unexpected results. And we do this through something called contagion analysis. And it looks like this. I have my little decomposition, my software, but it still suffers from the same problem. It's ordered inside a disordered system. Something is going to stress it. Something is going to hurt one of my components. And when this happens, we want it to affect as few components as possible. And so we use things like encapsulation and object orientation to try and put boundaries around our components. The problem is that in reality, when something unexpected happens, it usually hits more than one part of our system. And when this happens, in this case, the stressor hits component C and it hits component G, you can see in my component diagram that I didn't think these two things were related. I didn't think they were coupled. In network science, when you have this kind of relationship, the stressor's connected to C, the stressor's connected to G, it implies a relationship between C and G. And in our language, as software engineers, it means those two things are coupled. But we didn't know that coupling was there because we didn't know the stressor was there. And this is an invisible coupling. And it turns out when you do this kind of exercise that I've just described, you uncover a spider's web of invisible coupling in your application. This is what causes architectures to break apart and flake and give us unexpected results when we have contagion from errors. Since we know the functional relationships between our components most of the time, what we're actually discovering with these hidden links is non-functional requirements. This gives us a way as architects to get a better handle on what are the non-functional requirements in this system. It's much more effective than asking some poor stakeholder, what are your non-functional requirements, when they never actually understand that question. What do we do with this information? A really simple tool, which comes from the aerospace industry, something called the design structure matrix, which they teach at MIT. And we create something called an incidence matrix. And what we do is we put a list of all our potential components across the top, and all the X's that we came up with form every column. And this is our NKP analysis that we're doing now. And we go through this matrix, and every time one of these X's or stressors touches one of our functions, we give it a 1. If it doesn't touch it, we give it a 0. And this gives us an idea of which functions get hit by stress in this system and what are the relationships between these incidents. And what we get out of this is 7 different things that we can react to refactor our architecture. The first thing is we go for the large numbers. So you can see that there's a 5 up here on the first stressor. Why is that a 5? 5 is very high. It's a 5 because for some reason we've put all of our components on the same server, so when the server fails, they all go down. So let's change that. We've missed a residue here. Let's have some redundancy, or let's move these functions out to different machines. The next thing we notice is that down here, there's a 4. The stop charge command gets hit by a lot of stressors. That gives us 2 possibilities. One, this command, this function, is incredibly vulnerable and needs to be protected with redundancy and retries and all of that distributed systems kung fu that we love to do. Or our component, our function, is simply doing too many things and we've decomposed it wrongly and we've increased the attack surface for this function and we need to refactor and turn it into more functions. Another thing that we will notice is that some of our functions have 0 they never get hit by any form of stress. Again, there's two possibilities. One is that our function can never be damaged, never hurt. That's not possible. If that is possible, then you need to sell that, and you'll be in a different business. The other possibility is that you haven't stressed it. You haven't found anything that breaks it. You haven't thought hard enough. You haven't thrown enough darts at your system. Another thing that turns up here, which is really interesting, is that every row that has a value higher than 2 that has two ones in it, that's this invisible coupling. These two things are coupled to each other. Go in and pay attention to that. It might require a refactoring. And lastly, any two components, like these two here, that have exactly the same response to stress are going to live and die together, these two functions, all the time. Therefore, they can live inside the same component boundary. And this gives us a very repeatable and understandable way of setting component boundaries. Suddenly, our units become much easier to create. So we get a lot of value out of this one simple little matrix. Finally, we can do something that we've never been able to do before, is that we can show that as software architects, we've actually done something useful. What we have is a naive architecture. That's what we start off with. And we come up with a whole bunch of x's, this list of x's, and we produce, through our matrix, a residual architecture, a new architecture that's going to look very, very different than this naive architecture. What we do is we get another list of stressors, and we call these the red stressors, just because of the color of ink I chose when I drew this picture. And the red stressors, what we do is we take every single one of them and we run it over the naive architecture. And every time the naive architecture survives, we give it a point. And every time it fails, we give it no points. And we add up all its points and we call that number x. And we do the same thing to our residual architecture. And we run the stressors over it, we give it a point when it survives, and we add those up and we call that y. And then we calculate a value called the residual index, which is y minus x. So we're asking, is y bigger than x? Divided by the number of stressors in this red list, which gives us a value between -1 and 1. And if that value is greater than 0, then we have produced an architecture that is more likely to survive unknown forms of stress than our original naive architecture. We have made an improvement. We have done something useful. It turns out if you do this over lots and lots and lots of projects, you can actually run this as an experiment and produce a p-value to show that this is a statistically significant effect, that this is scientifically verifiable. This happens on a large enough scale for it to be considered reproducible. And that's a big step forward for us as architects. One final thing I'd like to say is that sometimes when I show these ideas, we can get some confusion because there's a tendency, a very human tendency, to look at new ideas through the lens of old ideas. We try to understand things by using analogies with other things that feel familiar. So there are some traditional methods that we use in architecture, things like risk management and edge cases and scenarios and requirements. And you might be sitting thinking, isn't that stressor list just a set of scenarios or risks? And we get this confused with risk management. The traditional methods are all about measuring, and they need to be accurate, and they need to be correct, and they need to be filtered. And we filter them usually by probability and by impact. And the point of these things is to give point predictions. This will happen with this probability, and we filter away everything with a low probability and a low impact. And the focus of these things is on one at a time resolutions of the ideas of every single problem. And the focus is on due diligence. And we tend to mix risk together. So we have project risk and financial risk and reputational risk and competition risk. And at the very bottom of that list is architectural risk, which nobody else in the business cares about except us. We're the lowest priority. It all gets packaged together in one movement. So Traditional risk management is not the same thing as what we've just talked about today. Traditional risk management is part of the problem. We're trying to get rid of this idea that risk has ownership and has impact and probability. Because one of the rules of the stressor analysis is that you're never allowed to talk about probability because it forces us into this little red circle. It gives us a skewed picture of what the circle is, because we're all throwing darts at the same place. We're trying to be accurate. It is not random. What we're actually learning about here today is the random simulation using stressors. We use many, many more points. There's no need for accuracy. Everything has a probability of 1. And it converges on a solution rather than producing a specification. What happens is that our architecture will actually emerge. And what we're trying to do is not survive one problem at a time. Our goal is to survive off-spec events and conditions, things that aren't talked about. And the focus here is on architecture, not on risk mitigation. We're not trying to mitigate risk. We're trying to produce a reasonable architecture in an uncertain environment. They're two completely different concepts. But some people who are trying to look at the new world through the old world lens get these two things confused. And so this is what we're doing here. This is the difference between the new world of random simulation and the old world of point prediction and risk management. We have to move away from this picture of mathematical correctness towards using these new tools. And it won't have escaped your attention that this particular test that I've talked about here mirrors the concept of training sets and testing sets in ML. We are now training our architectures, we're not designing them. This is an entirely different mindset than what has went before, even if that stressor analysis triggers in your mind a memory of a risk analysis register that you've seen somewhere that definitely will not have that line that says there's going to be mincemeat in the devices. This gives us an entirely new theory of software engineering, and that's really exciting. But it's not just theoretical, it actually provides concrete tools that solve real problems, which is what way is this system going to behave in terms of non-functional requirements. This forces you, as a technical person, to reach over the business boundary. You won't be able to talk about those X's if you don't understand the market and the business that you're working within. This stuff is properly researched. So I made a decision 6 years ago that I wasn't just going to publish a book or go on a speaking tour. I went back to university. I said, I want these ideas to be scientifically verified because it's time for software architecture to grow up. It's time for us to start taking things seriously and behave like all the other adults in the room. This is compatible with every other software methodology. There's absolutely nothing here that stops you doing anything that you're doing today. You will, even though I've been critical of risk management, you will eventually, after you've designed your architecture, do traditional risk management because that due diligence is still something your business has to do. It's just not connected to the design of architecture in the same way. This takes a lot of time to learn, so if you leave this room today and you feel like there was a lot of new words in there's a lot of new concepts, that was a lot in 1 hour, and it is a lot. This is going to take time to learn. This is easily bigger than OOP. There's a lot going on in here. There's a lot of moving parts. This is just an introduction to the concept. And one of the criticisms some people had of the ideas, and they were completely right, was that the academic articles that I've produced in the last 7 years are far too dense and far too heavy and far too academic to be read by developers and architects. And so this year I put together this little book which will help you to get a grasp of the ideas in a better way. It's a digital book. I have some physical copies here if you're interested. And that's everything from me for today. So thank you for listening and enjoy the rest of the conference. Thank you.